So we finished up looking at a well-designed experiment last time. And one of the things that makes for a well-designed experiment is random assignment. So if we can set up an experiment with completely randomized design. So completely randomized design. What we are doing here is making it so that all of the experimental units are assigned to the treatment groups completely by chance. Okay? And so if that is occurring, then you have what is called a completely randomized design experiment. So let's take a look real quick at the example that we have here. So pause it for a second and read the example here about the utility company. Okay, so now that you've read, the problem here is asking you to describe a completely randomized design involving 60 single-family residences in the same city whose owners are willing to participate in such an experiment. Write a few sentences explaining how you would implement your design. Again, we know how great sentences go on the screen here. So this one, again, to look at the complete word for word, is on page 246 in your book. Okay, so let's kind of talk out what we would need to do here. To do a completely randomized design, okay, like always, we need to label. So we would take start by labeling each house with a distinct number from 1 to 60. So every house is numbered 1 through 60. You could use your hat method now. You could use your technology. You could use Table D. Okay, in your book, it talks about using the hat method, taking 60 identical. So that's key there, that all the slips of paper are identical. 60 identical slips of paper, put them in the hat and mix them well. If you're going to describe the hat method, those are two things that you need to say. That the slips of paper are identical in size and that you mix them well before you choose anything. Those are two key components. Just like if you're going to do technology, you need to write the calculator command and explain what it means. Okay? If you're going to use the hat method, you need to say that the slips of paper are identical and that you mix them well. And then you could have somebody draw out 20 slips, and those slips of paper will correspond to the houses that will get a digital display. And then we'll draw out 20 more slips, and those houses will use a chart. And then 20 more slips after that where nobody is monitoring their usage at their house. And then we're going to compare those. Okay? What you need to keep in mind is don't start getting overly creative with how you are trying to randomize your design. You'll notice we haven't talked about rolling a die or flipping a coin or anything like that. We have talked about hat method, technology, and Table D. And you really need to just kind of stick to those. Okay? If you think about it, if you were trying to use a coin flipping method, it is actually different. You can't get a completely randomized design by using a coin flip. Remember, a completely randomized design is stating that all your experimental units are randomly assigned. Basically, it means that every single one of them had a chance to go in any treatment group that was available. So if I have, let's say I have all 60 families there, and each family is going to come up one at a time and flip a coin. And if they get heads, they get something to monitor their house. And if they get tails, they don't get something to monitor their house. And then once I have 30 people that have gotten heads, then everybody else, anybody that's left over, goes into the other group, the group that doesn't get anything to monitor. So what happens is you get the households that are flipping the coin near the end, they may never get to flip the coin, which means they did not have the option to be put into either treatment group. After the first treatment group was filled, they were put in the other. However, with the hat method, if I'm putting all 60 of them in there, I can pull out any of those 60. So even if I fill the first 20, all of them still had the chance to be in that first 20. Okay, so like I said, don't get overly creative with what you're trying to do here. Okay, you can use when you're writing and you're putting these things together on your exam, you can use diagrams and charts. If it will let me pull it over. here is an example of like a diagram or a chart that you could use. But one of the things you would need to keep in mind is that if you are describing an experiment, you may use the chart. Okay, so you can use a chart like this, but it cannot be the only thing that you do. You still need to write a few sentences to explain the diagram. So you can use diagram and sentences or just sentences, but you cannot use diagram alone. Now, a diagram may be helpful for some of y'all to kind of help it get your thoughts into place, help you kind of figure out exactly what's going on. I've got 60 houses, my random assignment. These are my groups here. Okay, these are the treatments that each group got, and then this is what I'm doing at the end. That's my response variable there at the end. So the diagram could be helpful to help kind of get your thoughts in place. Okay, so let's look at a few more examples. Go ahead and read the scenario, and then we'll talk about the randomized design and the purpose of the control. Okay, so let's talk about the first part here, the actual design of this experiment. So we want a completely randomized design for this experiment. So our goal then would be to randomly assign the 29 students to one of the two treatment groups. And remember, there are one of the two treatment groups. And our two treatment groups here are the ones that evaluate their performance in a small group and the ones that evaluate them in their performance alone. So remember, we need our context. You need to make sure you add your context there of what those two treatment groups are. Okay? And then our response variable is going to be the accuracy of their final performance evaluations. And so we need to describe how we're going to. We've got our replication covered because we have the amount of students here. We have our comparison because we have these two treatment groups that we're comparing. And now we would need to describe how we are going to assign them to their two groups. Okay, so one suggestion would be that you could take you could use your hat method, 29 slips of identical paper. Right, and you could put the 29 students on there, and then the first 15 that you pull are going to do it in small groups. Yeah, small groups, 14 of them do it alone. Or you could write on 15 slips of the paper, you could write small group, and 14 of them you can write alone and pass those out. It doesn't matter. You just need to remember that you've got your 29 slips of identical paper. You need to say what you're going to write on those, whether you're going to write, you're going to number off the kids 1 through 29, or like 1 through 15 is group, and then 16 through 29 is going to be the alone review of their taped performance. Hey, make sure you mention that you're going to mix those papers well. Okay, before they are then randomly chosen to be assigned to the treatment. Okay, the second part here is, what is the purpose of the control group in the experiment? Okay, the purpose of the control group in this experiment is the same as the purpose of the control group in any experiment. Okay, it is always to provide the baseline or that point of comparison. That is always the job of our control group. We need to establish what baseline, what normal is, so that we can have something to compare it to, so that we know if the explanatory variable is really making a significant difference. Okay, so let's look at some more things that can make an experiment just a little bit better. In an ideal world, an experiment is what we call double-blind. So in a double-blind experiment, the subjects nor anyone interacting with them and measuring the response variable knows which treatment was received. I think the easiest way to think about this is to think like physician-based experiments. Okay, and so if you're doing like clinical drug studies, the subjects don't know if they are receiving the placebo or the real drug. And the doctors that are treating them also do not know. And so that way, it's another way of maintaining control. Nobody knows, and so treatment is going to be the same. The doctor isn't coming in one day and kind of letting it show on their face that they know the person is getting the placebo. Okay, and so the person treating them, it keeps them treating everybody exactly the same because they have no idea who is receiving the placebo and who is not. And so that is how we can keep an experiment what we call double blind. Keep the subjects as well as the people that are interacting with them in the dark. Okay, so let's look at some examples of this. So, in an interesting experiment, researchers examined the effect of ultrasound on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound, the second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received the ultrasounds had heavier babies. So the first question is, did the experimental design take the placebo effect into account? Okay, so let's talk about that for a second. Okay. To take the placebo effect into account, we need a placebo. Okay? Was there anyone receiving a fake ultrasound? No. So the experimental design did not take the placebo effect into account. Okay? And it is not, the best way that this could have been done would have been to give an ultrasound, we'll use that term loosely, essentially some kind of fake ultrasound to the group that wasn't getting the real ultrasound so that they didn't know which treatment they were receiving. And this is important because, again, it can have an impact on the mental status. You could have had moms that were seeing their baby and so they were super excited, and so maybe that was kind of changing how they were taking care of themselves, and so they ended up with the heavier babies. Okay, so the next question then is asking, is this a double-blind experiment? Okay, so no, this is not a double-blind experiment. The moms knew whether they were getting an ultrasound or not. Okay, so it definitely was not double-blind. The people weighing the babies may not have known. The nurse that weighed the baby after the baby was born may have had no knowledge of the mom's ultrasounds throughout. But the moms knew, so it's not double-blind. The subjects knew. And this could have altered the outcome of our experiments because the moms knew if they were getting the ultrasound or not. They could have felt like maybe they weren't getting the care that they should have gotten if they weren't getting the ultrasound. Okay, there could have been a number of kind of mental things that come into play now. So here for number 3, based on our questions for 1 and 2, how can we make this better? And we already talked about this a little bit. So all mothers need some kind of ultrasound in this experiment. Okay, so treat everybody like they are getting an ultrasound. Okay, and then maybe for some of them we just don't turn the machine on. Okay, and then maybe you don't show them the screen so they don't know if the machine is on or not. And then the people that are weighing the baby at the end, then we just make sure they don't know whether they had ultrasounds or not. Okay, but that would be a way to definitely improve this, would be to make sure everybody was kind of exposed to the treatment or not. Okay, so let's talk a little bit about what we can infer from our experiments. One of the terms that you'll hear kind of thrown around loosely, and I will admit we throw it around loosely some in biology, is the term statistically significant. So when we're doing inference about these experiments, and we're trying to draw conclusions, in an experiment in particular, we're trying to show cause and effect. Remember, an experiment can show cause and effect where an observational study cannot. Okay? If something is considered statistically significant, the effect needs to be large enough that it would rarely occur by chance. As we get in basically the whole second semester, we will be doing inference. We will be doing a variety of testing to determine if something is statistically significant or not. Okay? At this point in the game, what we really need to realize is that results are going to vary. All of our results are going to vary by just a little bit because we're going to have sampling variability. If you think about the river activity that you guys were working on with the fields and the farmer, and there's 100 plots in the field. And if y'all are taking a random sample, if you're taking a sample from those 100 plots, everybody isn't going to get the exact same sample. But your mean yield should be approximately the same. It should be pretty close. Okay? And that would be due to sampling variability. Okay, samples from the exact same population, they can vary slightly because the sample isn't going to be exactly the same every time. And what we're going to learn to determine is whether that is what we call statistically significant. Okay, is the difference between the samples due to something, or is the difference between the samples just due to chance? Okay, and again, we'll look how to do that mathematically more later. We just need to kind of get a feel for the term now. Okay, let's take a second and read this example and get a feel for the scenario for a minute, and then let's kind of talk about what's going on here. Okay, so based on what you read here, what could they do to kind of take that into account? The fact that we have some people that are already familiar with a smartphone and some that are not. Okay, and so one of the things we could do is what we call blocking, or we could make our experiment have a randomized block design. I think of a block design as kind of similar to when we were stratifying with when we were taking surveys. Okay, when we were sampling for surveys and we were stratifying or making those groups that had something in common before we then started surveying the group. Okay, so if we look at our definition for a block is our group of experimental units that are known before the experiment ever started, that are similar in some way, and that particular way could affect their response. Okay, if they're similar in some way in the sense that we're talking about whether they should use this keyboard or not, and all are girls or all are guys, like that's not what we're talking about. We're talking about they have some kind of experience that could give them a leg up in this. Okay, and so that would be being used to the smartphone or not. So in a randomized block design, we form the blocks first, and then we randomly assign the subjects or the experimental units to the treatments. So something that we need to keep in mind is that our treatments are not the same as our blocks. Let's take a look at this for a second. Let me just move this over here. So let's kind of look at a diagram of this experiment here, of this experimental design. So we have our 10 volunteers right here. Okay, and this right here, these are our blocks. This is not random. They are not assigned to a treatment group yet. They are assigned to a block. They use a smartphone or they don't. Over here, these are our treatment groups, okay, whether they're getting keyboard A or keyboard B. Okay, and so our random assignment happens as we go into those treatment groups. That's where the random assignment goes. So they were on purpose put into groups of smartphone users and non-smart users, and so that's our blocking part of it. And then we randomly assigned them to the treatment groups, and then after we compare our typing speed, we can combine the results back together again. So pay close attention to your language that you're using. Okay, it is important that you are not mixing up your language. The tip here is talking about your language of experiments versus your language of sample surveys or observational studies. You cannot say you have a randomized block design for a survey, nor can you say that like your experiment has non-response. So we really need to make sure that our vocabulary is sorted out. What goes with sample surveys, what goes with experiments, and what goes with observational studies. Okay, so let's look at this blocked example. Again, this is going to be on page 254 if you want to see the full-blown, word for word solution here. Okay, so we've got women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of 3 advertisements for the same product. So the first question here asks to explain why a randomized block design might be preferable to a completely randomized design for this experiment. So you're not explaining how you're setting up the experiment here. You're explaining why you would form these blocks here of women versus men. And so if I had a completely randomized design, I've got men and women all together as a single pool. And so we could end up with one treatment group maybe getting having like all women or a very large amount of women, or one treatment group having a very large amount of men. And what this does when this happens is we lose our... We're not taking into consideration the fact that we know here that men and women respond differently, that they respond differently to advertising. And this whole study is trying to see which kind of ad is the most effective. Okay? And so when we put everybody into the same pool, we lose that, we run the risk of losing that getting kind of lost in the shuffle. Like I said, again, if we had a group that was all men or all women. Okay, so part B there has us outlining a randomized block design using 300 volunteers. Tells us we have 180 men, 120 women. Okay, and so remember this part right here is non-random when we are putting them in their blocks. Okay, where this over here, these are our treatment groups, right? Their treatment is which ad they are receiving, ad 1, 2, or 3. So those are our treatment groups, and those are randomly assigned. So we block the 120 men and 180 women first, okay? And then we need to describe this random assignment here. You would need to describe that, using hat method, using technology, but you would need to describe how they're going to split that group of 120 women. And you would need to describe how you're going to split that group of 180 men. One type of randomized block design that you could see is what we call a matched pair design. So a matched pair design it's a form of blocking. So you're creating blocks, and these blocks, you're basically taking pairs that you're trying to put into these blocks. You're trying to create blocks that have matching pairs of similar experimental units. And basically what happens here is that each pair is going to get the treatment. Basically, it allows you to be comparing the two pairs to one another. Sometimes, and a lot of times actually, a matched pair design is done with just one subject. And that one subject is exposed to both treatments. And you have to randomize, if that is the case, you have to randomize the order of the treatments, because the order could influence their response. But basically you have, let's say you're using a person, the one person gets exposed to one treatment group, and then that person gets the second treatment. Okay, and it allows you to kind of compare the two to one another. We'll look at some examples of this, later. Let's look at this example here. So you've got it tells you here you have a Fathom dot plot. Okay, Fathom is just the software that was used to create this. So you have a Fathom dot plot of pulse rates for their completely randomized design that is shown below. Okay, you've got a pulse rate, a mean group. You're looking at the mean of a group that took their pulse while standing, and the mean of a group that took their pulse while standing. Okay, so if this was a matched pairs experiment, you would have every person, let's say our class was doing this experiment, all 19 of you would take your pulse standing, and all 19 of you would take your pulse sitting. You'd be exposed to both treatments, and then you would compare the two. And okay, the last thing we want to look at is what can we do with this information? What kind of inference can we use? How far can we take this? Okay, so one of the things we would need to, this chart here kind of summarizes what we would need to know about the design to determine what we can infer. So looking here across the top, we have, are the individuals randomly assigned to groups? Yes or no? And then on the side here we have, were the individuals randomly selected? So if you get yes about both of those, randomly assigned to groups and randomly selected, you can make inference about the population, because that would be your randomly selected part. Okay? And if they're randomly assigned to groups, I can make inference about the cause and effect. Okay? So this tells us if I can make inference about the population. This tells me if I can make inference and effect. Sorry about the slide jumping there. Okay, so over here, like let's say your individuals weren't randomly assigned to groups, they were not randomly selected. You cannot make any inference at all if there was no randomization. So let's look at an example of this and kind of look at 4 different scenarios that we have here. Okay, this one, again, following along in your book. This one would be, it starts on page 267 and carries over to page 268. So, page 267 and 268. So, what we have here is a dentist, and he's trying to determine if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C at all. Okay, and so he's got 4 possible studies for his design there. And the problem there is, what can the dentist conclude for each design? So let's take a look at each one. So design number 1, he's got all the dental patients in town with appointments in the next 2 weeks to take part in a study. Give each patient a survey with the 2 questions. Okay, do you take at least the 500 milligrams of vitamin C each day? Do you frequently have canker sores? Based on the answers to question 1, divide them into 2 groups. Those who take at least 500 milligrams of vitamin C and those that do not. Okay, these patients were not randomly selected. Okay, he just took all the patients that were coming in the next 2 weeks. So they were not randomly selected. So, which means then he cannot make inferences about his larger population of patients as a whole. This was an observational study. There was no treatment imposed on the patients. He did not say, you will take vitamin C, you will not. Okay, so there was no random assignment to groups either. So this dentist officially also cannot make any inferences regarding cause and effect. Okay, so design number 1 is really not so great. No inferences about the population, no inferences about cause and effect. So let's look at design number 2. So in design number 2, he's got all the dental patients in town with appointments in the next 2 weeks to take part in a study. Randomly assign half of them to take 500 milligrams of vitamin C each day and the other half to abstain from taking vitamin C for 3 months. Okay, so once again, nothing about the population because these were not randomly chosen. Okay, but he could possibly make some inferences here about cause and effect because they were randomly assigned to treatment groups. So he could make some cause and effect inference. Okay, design number 3 here, he's selecting a random sample of dental patients in the town and get them to take part in the study. Okay, so he can do observations now. He can make inference about the population because he randomly selected the dental patients and get them to take part in a study and then divide the patients into 2 groups as in design number 1. Well, in design number 1, they were not randomly assigned to the groups, so he cannot do cause and effect for design number 3. For design number 4, he's selecting a random sample of dental patients in town and get them to take part in the study, so he can make inferences about the population. Randomly assign half of them to take vitamin C and the other half to abstain from taking vitamin C. So now he can do cause and effect inference as well because they were randomly assigned to the treatments. So that would kind of be his best bet if he wanted to make both of those types of inference. So that's it. That's where we're going to stop now for chapter 4. Okay, and we are all set with this designing studies chapter.